Good morning. Welcome to MFC Group's FasTech seminar series hosted by EAS Sales, FH Sales, Mel Foster, and TMC. Thank you for joining us. Today we're featuring Making Sense of Surge Protection with Littelfuse. Our speaker for this seminar is Mark Hubbard, Field Application Engineer for Littelfuse, based in Chicago. Mark joined Littelfuse in 2000 as an application engineer in the electronics business unit focusing on circuit protection solutions. For the last 14 years, he has been responsible for providing technical support to customers, driving new business opportunities, and delivering technical trainings for the Midwest and Northeast regions of North America. He received his Bachelor of Science degree in Electronics Engineering Technology from Purdue University. And Mark is a great resource for us for the MFC group and works closely with our customers and is always happy to support. Everyone's muted for now, so please type any questions you may have during the presentation in the chat, and we'll monitor the questions throughout the presentation and answer them at the end. And be sure to stick around for a fun round of trivia at the end where the top three winners will win a prize. Just a disclaimer, if you're not allowed to accept a prize, you're still welcome to participate and have fun and then decline the prize at the end. And with that, Mark, I will turn it over to you.
Thank you very much, Amanda. And thank you everyone for joining today. And I appreciate the opportunity to present to you today. And as Amanda mentioned, the topic today is going to be making sense of surge protection. So what we're going to go through is we'll talk about some transient threats. We'll get into some detail about typical components that are used to help mitigate transient threats. And then at the end, we'll talk a little bit about how maybe we can use some of these components to enhance or optimize circuit protection from transient events. But first, we'll talk about the transient threats. So about 75% of all equipment failure is due to an electrical overstress caused by a transient event. Semiconductors are more prevalent and increasingly intolerant to transients. And transients can be caused by different atmospheric type of events. So on the very heavy side or large energy side, we have lightning strikes. Now, if you have a piece of equipment and it's struck by a direct lightning strike, honestly, there's really not much you can do at a equipment level to try and protect it because there's just too much energy to try to handle. But what we really try to prevent damage from occurring is when we have induced lightning strikes or proximity strikes. And these are lightning strikes that it can occur several miles away, but can induce transient into the cabling, whether that's above ground or below ground, and then transmit that transient energy down the cable to the end equipment. And this type of an event can be in thousands, in some cases, maybe even 10,000s of amps that need to be handled. Another type of transient event is a switching surge. So turning on and off large inductive loads, such as industrial motors, can cause transient events on cabling. And these can result in large voltage spikes because of the inductive characteristics of the circuit and the cabling. And not only is that line affected where the switching occurred, but these events can also be induced onto cables that are run in proximity to the line that is affected. Now, this isn't quite as high of energy typically as, say, a lightning strike, but it can still be very high energy events and can cause damage to end equipment. And then the final transient event is ESD or electrostatic discharge. Now, this is a very fast event, and as you'll see, it has a very fast rise time and occurs very quickly, especially compared to these other events. So it's very low energy. However, it can be extremely high voltage in the thousands and in some cases even tens of thousands of volts. And this can cause anywhere from soft failures to resets and even to hard component failures. And failures can occur in equipment or in, say, driver ICs or chipsets at levels at 2 kV or lower. But in the environment, we have much higher type of transient events starting typically at around 8 kV, or at least that's where most customers begin to test, all the way up to even 25 kV in some cases. So obviously we need to have some additional protection to ensure that we can protect these systems from an electrostatic discharge event. So there are several standards out there that provide guidance as well as information on how to test or evaluate end equipment for these events and how best to simulate these type of atmospheric events. The first one on the left-hand side here. So this is an ESD event. And for end equipment use, the most common standard that's used is the IEC 61000-4-2. It's the one that's most commonly referenced. And this has a wave shape, a very fast rise time of less than a nanosecond. And the whole event occurs in typically less than about 100 nanoseconds. So very fast event. And test levels can range anywhere from 2 kV to 8 kV. And then in the standard, there's also an X level, and this X level provides the manufacturer to test their equipment at a level above what the maximum level is within the standard. In a lot of cases, customers are going to 15 kV, 20 kV, and so on. The load switching standard, the most common one used here, is the IEC 61000-4-4. And this consists of very rapid pulses, but they are grouped together in what's called a burst pulse. And so this actually provides a little bit more energy than you would see basically in your ESD type of event. And these voltage levels can range up to 4,000 volts and have considerable amperage involved with them. And then this is reoccurring. So this is essentially to try to simulate contact bounce within a switch. And then for lightning events, there's a few different standards. For globally, the typical standard that is referenced is 61000-4-5. In North America, there's some other standards that are referenced, typically IEEE C62 or UL 1449. Now, the test waveform that's typically used, especially if we're talking power circuits, is what's called a combination waveform. And the combination waveform consists of an open circuit voltage waveform, which has a 1.2 microsecond rise time to a 50 microsecond fall to half peak. And then it has a short circuit current waveform that consists of an 8 microsecond rise time and a 20 microsecond fall to half peak. Now, there are other waveforms that are used. There are certain components that are referenced, different waveforms, telecommunications systems kind of have their own different waveforms that range anywhere from a 10 by 1000 microsecond waveform to a 2 by 10 to a 5 by 350 and so on. Now, the voltage levels that can occur in these lightning events or in these test simulations can range anywhere from about 1 kilovolt, some cases 500 volts, but then all the way up to a 20,000 volt event. And this can result in anywhere from 500 to 10,000 amps of transient current. So this is a lot of energy to try to handle and make sure that we're not resulting in damage to the end equipment that we're trying to protect. So now we'll talk about some of the components or common components that are generally used to mitigate these type of events. And there's really 4 main technologies that are used most often, especially at a board level protection or end equipment level. And these are metal oxide varistor, transient voltage suppressor, a gas discharge tube, or a high power side actor, or what's called a protection thyristor. So each of these components kind of have their advantages and disadvantages over the other. But first, we'll talk about how a suppressor is generally connected and used. So a suppressor is typically placed across the line, and then during a transient event, it will change its resistive characteristics and begin to conduct current and redirect it away from the protected circuit or protected electronics, and basically mitigating the amount of energy that comes from the transient that would actually reach the electronics. And there's 2 basic types of suppressors in the industry. The first one is called a clamping device. Now, a clamping device, when a transient occurs, it will essentially chop off the top portion of this transient event, and that energy will be absorbed within the suppressor. So it holds the voltage level at a point that is above the operating voltage of the system, but ideally below the damage threshold of the circuit that you're trying to protect. And then once the transient dissipates, it will go back down to normal operating voltage levels. And here's an example of a VI curve for a typical clamping device. So you'll have very low leakage under normal operation, and then once you reach a breakdown voltage, you'll have a non-linear characteristic that will have very minimal change in voltage over a larger change in current. Examples of these types of devices are going to be metal oxide varistors or TVS diodes. The other type of technology is a crowbarring device. And how a crowbarring device works is once you reach a certain switch voltage, the voltage will actually drop to a near zero or very low voltage level that is some level below the operating voltage of the system. And then once the transient dissipates, it will delatch and go back to normal operation. And here's an example of a VI curve. This is actually for a sidactor. So you can see once you reach a certain voltage level, the voltage snaps back and we have a very low voltage level over a change in current. Now, one of the caveats to these devices is that if there's enough energy to be supplied after the transient goes away, it may stay latched in this conductive state, which is not a good place for them to be. They can't handle energy for a long period of time. So these are typically used in more high impedance line type of applications or telecommunication type of circuits where clamping devices are typically used in power. There are some exceptions, but generally that is how they're used. Now, as far as their capabilities are concerned, they do have some advantages and disadvantages, and I'm going to highlight a couple here. And the first one is going to be the let-through voltage. So how well is it protecting? How tightly is it clamping? MOVs have a somewhat higher clamping voltage, and GDTs take a while to kind of get going and will have a high let-through before they crowbar into the crowbar state. As opposed to TVSs or sidactors that actually have very excellent performance in the way of clamping performance or their VI curve and provide a much better level of protection or reduce the amount of let-through that gets to the end circuit. However, the flip side of this is the surge dissipation level. So both MOVs and GDTs have very high surge capability in the thousands of amps or even tens of thousands of amps range. So they're very good for high energy lightning strike type of events. Whereas TVSs are typically very low. Generally, they're going to be, I would say, in the tens to hundreds of amps. In some cases, we can get to kiloamps, but those are kind of the exception. And same thing with sidactors. We're probably in the hundreds of amp range, but we do have some exceptions that get into those higher voltage or higher current levels. And then the last one I'll talk about is pulse cycle capability. Both MOVs and GDTs have a wear-out mechanism, so they can only handle so much energy for so long. Whereas TVSs and sidactor devices are both silicon-based, so they have very excellent pulse cycle capability. So I'll talk a little bit more about varistors. So a varistor is essentially varistor is short for variable voltage resistor or voltage variable resistor, and it essentially acts like a back-to-back zener. It's made of an zinc oxide powder formulation, which is centered into some sort of a shape, whether that's a circle or a block, depending upon the type of device we're trying to create. And this creates a series parallel matrix of grain boundaries. And the voltage within these grain boundaries is dependent upon the voltage gradient, so which is basically the voltage per millimeter of grain boundaries that exist, which essentially results in the greater the thickness of the part, the higher the voltage rating of the part. And there's also in the parallel form, that's really what dictates how much current it can conduct during a transient event. So the more parallel paths there are, or the wider the disk, the more energy it can handle. And this is a typical VI characteristic curve of an MOV, and this is its equivalent circuit model. And basically what we have here is in the leakage region, we're in a linear state or ohmic state where we have very small amount of current being conducted over a change in voltage. So the Rx value is typically ignored because R off is going to be the predominant resistance characteristic. In normal varistor operation mode, this is when we enter the nonlinear or clamping portion of the curve. And at this point, Rx begins to reduce by many degrees of magnitude, which then becomes more predominant than R off. So it becomes the more predominant resistance in this particular portion of the curve. And then finally, we end up in the upturn region where we've kind of reached the based resistance value of the grains that exist within the product itself, which is our R on value, which ranges generally anywhere from about 1 to 10 volts. And then we start to enter again into more of a linear operation of the part where we have a more drastic change in voltage over current. Another key characteristics of MOVs is this pulse cycle limit, and this is represented by pulse cycle capability curves within the part. So, and all of these are located on the data sheet, and each curve typically represents a family and a size within a series of MOVs. So if we look at this curve, we see that for this particular one at 10,000 amps, it can handle a single pulse one time for 10,000 amps for a 20 microsecond waveform. So that relates back to that 8 by 20 microsecond. Now, if we decrease the peak current, say to 1,000 amps, then we can handle up to 500 pulses. So we have a much greater pulse life for lower peak current values. But this also does change as we increase pulse duration. So as the pulse duration increases, the capability begins to decrease. So these are all factors that need to be taken into consideration when we start looking at selecting MOV products. So a key aspect here is determining how much current and voltage are going to occur across the MOV under a given transient for a given varistor. And there's really two methods of trying to determine this. The first one is a calculation method. So if we know the peak transient voltage and the source impedance, we can estimate what the current will be using Ohm's law to determine what the peak current would be through the MOV. From this, if we reference the VI curve of the MOV, we can get an estimation as to what the peak clamp voltage would be under that condition. Now, that's assuming that the MOV is a short, which it is not. So what we typically do then is we recalculate the peak current by taking the open circuit voltage minus the clamping voltage that we determined from the curve, and then dividing that by the series resistance, and that gives us a different clamping voltage. And then if we do this a couple of times, we'll get a pretty good estimation as to what we can expect. Another method is to use a graphical method. So this graphical method is we plot the load line of the transient from the open circuit voltage to the short circuit current and plot that against the VI curve of the MOV. And where the two intersect will provide us both the estimated clamping voltage as well as the estimated peak current. And then we'll be able to determine if this is going to be appropriate for our application to make sure we have enough low clamping voltage as well as enough surge transient capability from that MOV. All right, so the next device I'll talk about is a TVS diode. So TVS, or transient voltage suppressor, also referred to as a silicon avalanche diode, or SAD, has a silicon-based construction, so it has a PN junction that operates in the avalanche mode. If the device is forward biased, it will break down at about 0.7 volts and begin to conduct electrons. If it's reverse bias, it will hold off current until it reaches a breakdown point or a breakdown voltage, at which point it will begin to conduct reversely through the TVS diode. Now, these come in a couple of different options. So whereas an MOV was only bidirectional, we have unidirectional options, kind of as I described, or bidirectional options, where whether it is forward or reverse bias, the breakdown voltage is going to be dependent upon the characteristic of the TVS and the breakdown voltage rating of that particular TVS. Now, the nice thing about these devices, and I mentioned this before, is they have a very tight clamping performance. Some key characteristics for a TVS diode. So here's an example of a unidirectional VI curve. So the VR, or standoff voltage, needs to be greater than the operating voltage of the system. The VBR, or breakdown voltage, is the point at where it transitions from the low current state into its linear state or nonlinear operation state. And this is typically specified at a given current value. And then the VC is the maximum clamp voltage given at a specified peak current. Now, if we take the product of that clamp voltage and peak current, that would provide us with the amount of power that is dissipated within that TVS. And so those values typically will equal the power capability of the TVS of that series. And power is a very key parameter. Now, the power in this case for most TVS diodes is based on a 10 by 1000 waveform. So that in this case is 400 watt. But as we can see by the peak pulse power curve, if the duration changes, the power capability changes. So shorter durations, we have higher power capability. Longer durations would be less power capability. Now, the other thing about this is all of the TVS, the peak pulse power capability is dependent upon chip size and package. So therefore, the power rating is common within a series of TVS diodes. And what this basically results in is that lower voltage rated TVS diodes will have higher current capability, and higher voltage TVS diodes will have lower current capability. And this comes into play if we need to do things like series stacking or what have you. So how do we determine what power capability we need? So we basically start by the power calculation. So if we know the peak voltage, if we know the series resistance, we can determine an estimated peak current, kind of like we did for the MOV. Once we have this information, we can estimate what the clamping voltage would be based on, what the peak current would be based on Ohm's law. Now, once we know the peak current, then we can determine what the peak clamping voltage is going to be. And this is done with something referred to as dynamic resistance. And dynamic resistance is basically the resistive characteristic in the nonlinear state. And this can be calculated using values from the data sheet. So it's basically the peak clamping voltage minus the breakdown voltage divided by the peak current provides us with the dynamic resistance. So if we take that dynamic resistance multiplied to the peak current that we determined earlier, and then add that to the breakdown voltage, we can come up with a peak clamping voltage. And then by taking those values and multiplying that peak current and that peak voltage, we come up with the estimated power dissipation that's required so we know what size of MOV that we need. So the next device I'm going to talk about is a gas discharge tube. So a gas discharge or plasma device acts like a voltage-dependent switch. So it's a hermetically sealed chamber that includes or contains an inert gas with some outer and inner electrodes. And these can be either 2-terminal or 3-terminal devices. So how they operate is once the voltage exceeds a certain breakdown voltage, it ionizes the gas internal to the chamber and then creates an arc that jumps across the inner electrodes. And this causes the voltage to drop to somewhere about a 10 to 35 volt range. And then as the transient dissipates and the current drops below a given value, the arc will suddenly stop and the event will extinguish, and then the device will go back to a high voltage condition and low leakage current. And these devices, as I mentioned, can handle fairly high currents, anywhere from about 5,000 amps to about 20,000 amps for a typical 8x20 waveform. Key features are they have very low leakage, and they also have very low capacitance. Now, the response time is kind of a key thing to take into consideration when you're looking at GDTs. And this kind of breaks down into two different states. The first one is the static response state. And this is typically characterized using a 100 volt per second rise time waveform. And this is also referred to as the DC breakdown voltage or DCBV or VSDC. Now, when you're selecting this device, the minimum value of this DCBV needs to be greater than the maximum operating voltage of the system. Otherwise, there's a potential for a false trigger. The other characteristic is the dynamic response. And this is also referred to as impulse spark over or breakdown voltage. And this is characterized using 100 volt per microsecond or 1,000 volt per microsecond typically. And this represents more of the protection level or the let-through voltage that could be seen by the circuit. And this occurs under ultra-fast type of surge event or with a fast rise time. And you can kind of see the difference here as the response time decreases, but the let-through voltage increases depending upon the rate of rise of the transient event. So GDTs in general are slow reacting and result in higher peak voltages under fast rise surge events. The last technology I'll talk about is the Protection Thyristor or Sidactor. So as mentioned before, they act like a crowbar device similar to that of a GDT. And they're basically a self-gating triac device. Historically, these have been used in more telecom systems to help protect customer premise equipment or central office equipment to kind of deal with the last mile, where you have, you're running copper from a distribution point or what have you that are susceptible to transient events or lightning events for end equipment. Features for this are applicable for both surges as well as long-term temporary overvoltage or voltage swells, as long as they're designed appropriately depending upon the affected swell. They have very fast response time, so they're probably the fastest responding of the technologies that we've talked about. They also have very low overshoot or let-through because they respond very quickly. Very low on-state voltage, even lower than that of a GDT, and they do not degrade after multiple surges over time. So you can essentially surge them as many times as needed, and you typically will not result in degradation of the part. So the next thing I'm talking about is some combinations. So the first combination I want to talk about is that of an MOV with a TVS diode. So as I mentioned, TVSs have very low clamping performance, whereas MOVs have high clamping performance, but MOVs are much higher energy. So by using the two in combination, you can improve the let-through performance while still maintaining high surge capability. And they're typically used in what's called a pi network. So this is where you have an MOV across the input, and this is what is designed to handle most of the energy. So it needs to be selected to be able to handle the amount of transient energy that is expected. And then we have a TVS on the secondary side, which reduces the overall peak let-through voltage. However, for this to operate properly, we have to have some coordinating impedance in between. Otherwise, the TVS will turn on first and take most of the energy. So by using an inductor, something like an inductor in between, the LDIDT characteristic of the inductor creates a voltage divider circuit so that most of the current energy is forced through the MOV, less is applied to the TVS, and the TVS then provides a lower clamping performance. Another combination is some applications require an isolation. So an MOV typically, in some instances, should not be connected to ground. And there are certain areas of the globe where this is actually not allowed. So how to get around this and still provide adequate surge protection is to use an MOV in series with a GDT, because a GDT has very low leakage and very good isolation. So connected in series with an MOV, it will ensure that the GDT also shuts off once the transient event dissipates. So the resistance of the MOV will limit the amount of follow-on current and ensure that the GDT will shut off. Now, since most of the voltage appears across the GDT due to the capacitive differences of the two devices, the standoff voltage of the GDT needs to be designed so that it is greater than the peak AC voltage of the AC mains waveform or AC mains voltage. Now, you can also reduce the MOV, because now that you have this higher standoff with the GDT, you can actually reduce the rating of the MOV and help improve clamping performance or reduce let-through. Because once the GDT fires, most of the voltage that's going to get through is going to be a result of the clamping voltage of the MOV. So that can be reduced by reducing the MOV. However, there is a practical limit that you can go to. Otherwise, you're going to still end up with some follow-on that's going to go through the GDT. So there is a practical limit that you can go down to, but we can help design for that factor. And then the last one I want to talk about is using an MOV and a side actor in combination. Now, we do offer some high power side actors that are in the thousands of amps that are similarly rated to certain MOV devices. Now, in some cases, we've seen where the clamping voltage of an MOV is not sufficient enough to protect certain semiconductor components. Other ways around that is you have to start paralleling several MOVs to try to help reduce the overall clamping performance. But a more efficient method of doing this is by combining it with a side actor. So if we look at the curves of the MOV and the side actor, we see we have a clamping and a crowbar. So by adding the side actor in series, the standoff voltage is a combination of the two. So we can actually reduce, again, the voltage rating of the MOV. So we end up with a curve that looks a little bit more like this. So we still have kind of a fold back feature that occurs. So once the side actor reaches its breakdown voltage or switch voltage, it will drop down to essentially the clamping voltage of the MOV. So we can reduce the overall let through energy that occurs within the MOV. And there is a link, there is an application note on our website that goes into more detail about how this works. So to kind of illustrate a little bit the performance improvement, if we were to take a 275 volt MOV and apply an 8x20 6 kV voltage to it, we'd end up with about 876 volts. If we use in combination with a side actor, we can drop this down to about 175 volt rated MOV. And you can see the reduction is now down to about 645 volts let through. So much improved performance as far as let through is concerned. And we've also seen some improvements in leakage current as well as multi-pulse capability. Because the side actor actually does have lower leakage current than the MOV, the overall leakage current at a given voltage is reduced, and we also see a minimal change in leakage current over multiple strikes. Same thing with the breakdown voltage. So we actually see less of a change in the overall breakdown voltage, so less degradation over time or over multiple pulses of the MOV than we see in just an MOV alone. And then this is just an overall product portfolio slide to give you an idea of what we do, not just in circuit protection, but also other technologies, other options that we often offer even beyond circuit protection technology. And then, of course, we have collateral material. This electronics catalogs.littelfuse.com is basically a reservoir of all of our product catalogs, application notes, design guides, what have you. So I encourage you to visit that and look up our material. So that was the end of my presentation for today. So at this point, actually, I will turn it back over to Amanda.